The formulas that we came up with for the orthogonal projection and orthogonal complement look a bit strange. They aren't obviously linear, I guess is what I'm trying to say. Right? When we're doing linear algebra, we'd like for things to be linear, but this isn't obviously linear because of all the dot products, right? It's possible for some operations involving the dot product, it's possible to get nonlinear results because you're multiplying things by other things. And sometimes that gives you nonlinear results. Sometimes it gives you quadratic results. But what we could try to do to decide if this is linear is try to come up with a matrix for this as a linear transformation. Now, in this setup, we're holding u fixed, right? So u it's a vector, but it's not our variable vector. So when we do this projection, what we're talking about is this transformation, projection sub u. So this is going from Rn, right? Because there's a space to put the vector v in here. So this is going from Rn, and what it produces is another vector in Rn, right, which is the projection. The only question is, so this is a perfectly well-defined function. Here's a formula for it. But the only question is it linear? So let's see if it's linear by trying to come up with a matrix for it. So u is, right, this u right here, that's just some vector, and it's a fixed vector, right? The only variable in this formula is v. So let's move the u over to here just because, well, you'll see why in a minute. v dot u over u dot u. And v dot u, we can write this as, instead of v dot u, we can write it as u dot v, right? The dot product is commutative, so I can write it the other way if I want. And remember, one nice way of writing the dot product is that it's actually the first vector transposed times the second vector. So this is u transpose v, okay, over u dot u. Okay. Well, this over u dot u, that's really just a scalar, right? That's 1 over u dot u. And u is a fixed vector, so 1 over u dot u, this is just some number, right? It's a scalar. So times u, and then the stuff that's left over is u transpose v, right? So this is 1 over u dot u times u transpose times v. Well, look, this projection, what it does is it takes v and it sends you to the projection onto u of v. And what we found is, right, to get the projection, you take your vector v and you multiply it by this. But this is a matrix, right? This, since u is n by 1 and u transpose is 1 by n, this whole matrix is n by n. So this matrix is a linear, or represents, a linear transformation from Rn to Rn, and it's the linear transformation that takes v to the projection onto u. So this means that this orthogonal projection is linear because, look, it has a matrix. It must be linear. So that's kind of a non-obvious fact, but it's kind of nice. And in fact, right, not only did we show that it's linear, we have an explicit formula for the matrix that does this projection. It's just 1 over the magnitude of u squared times u transpose. It's kind of, this, I think this is maybe the first time where the transpose of a matrix has come up in sort of a natural way, right? Whether you consider writing the dot product in terms of a transpose natural or not is maybe a matter of opinion, but writing the projection, the matrix of a projection, this definitely is something that is natural and not contrived in any way. So it turns out that this is really where the transpose matters when you start working with the dot product. All right, so that's all for the orthogonal projection. What about the orthogonal complement? Right. If the orthogonal projection is linear, then we sort of strongly suspect that the orthogonal complement is as well, but how could we How could we prove it? Well, this right here, that is the orthogonal projection, right? So we are just trying to come up with some, what we're trying to do is come up with some matrix so that V perp is that matrix times V, right? But we have V sort of spread around in too many places here. We want to write all of the V's as, wherever V shows up, we want to write that term as some matrix times V. So for this first part, what matrix do you multiply V by to get V? Well, the identity matrix, right? The n by n identity matrix, okay, minus, and then this second term is just a projection, and we already have a formula for the projection. So that's 1 over u dot u times u transpose V. But now both of these, since both of these are written as the vector V times some matrix, where the V is on the right-hand side of the product, we can just factor out the V. So we get I minus 1 over u dot u, u transpose, all times V. That means this matrix, this is the matrix that does the orthogonal complement. So this matrix is the linear transformation from Rn to Rn that sends V to the orthogonal complement of V relative to U. Okay. So both of these operations turn out to be linear, which is nice, and they both have pretty nice expressions for the matrix that produces these operations.